students with me.
Students, alors, le roi Hubert. Thanks.
One. And yeah, it's marked. Something should be in order. Mais à online. Do not ignore my list.
Thank you.
Yeah. Okay, here we have something. So, it's time.
J'espère pour le rapport de crampage du.
Ah oui, j'espère aussi, mais je pense qu'il y a le
Mais juste cliquer si ça renvoie vers un
ouais.
sérieux.
Hello.
Ah, sorry.
We are online, everybody watch us. All world watch and listens. What I have for today. Last time we speak about amplitude modulation, yeah? I have a source of signal, this large generator. It produces rectangular pulse with the frequency, not pulse but periodic signal, with the frequency 405 Hertz. See? So, I have approximation of something like this. It's my signal with the frequency, okay, 405 Hertz. What spectrum will it have? Can you tell me what will be spectrum of this signal?
3 straight lines.
3 lines. One at, let's say, 405 Hertz. It will be, let's say, 100%. 33% will be at which frequency?
At 1/3 of 130.
That means triple, not 1/3. It will be 3 by 5, and we also will see 1/5 or 20% at 5 or 5. It's a spectrum of this generator signal. 3 frequencies. Now, what I'm doing? I use this signal, this thick wire, to drive this generator. This is a generator of test signals from receivers. What I have? I have signal cosine omega 0 time with omega 0 being approximately by 600 kilohertz. It's a carrier. I can disconnect. Okay. This is carrier. I need to, I can show it well if I do something like this. This is carrier signal. I have disconnected the transferable signal. So I have source. I have, let's say, controllable amplifier. This is, here we have frequency omega 0, and signal will control, this generator signal will control gain. As a result, what will I get? Multiplied by modulation depth, cosine omega 0, or amplitude modulated signal. Connected. Do you see it? Here is high frequency signal, but amplitude is changes with the law of transferable signal. 1 second, where are you? Here, the red line is a spectrum of this signal. Red line is a spectrum of this signal. So what I get? Here is a function of time. If I perform a spectrum analysis, I'll get, in theory, one line at omega 0. Yeah? And omega 0 plus 4 or 5. Omega 0 plus triple or 5, omega 0 plus 5 multiplied by 5. Is it clear? We saw it. And the same thing, this one is omega 0 minus our 4 hertz. This one omega 0 minus triple of 5, and this one will be omega 0 minus 5 time of our 4 or 5 hertz. Maybe with Hammond law. Now it's seen better. Did we show something like this before? Yes, it's an amplitude modulated signal at a frequency at this moment approximately 600 kilohertz. I have this device. It's an interesting device, and it illustrates quite old but still popular technology. What's the idea? Let's see what will be if we perform a sum with a special local generator called heterodyne. With the frequency Fr. It produces just something. I have voltage occupied, cosine, double P, and hash. It produces something like this. And now question from the school. Let's start from the very simple. Pure sine. What will be sum of two cosine functions? Cosine alpha plus cosine beta equals to what Google can say as sum of cosines produces idea. See? One second, I'll show one thing. Let's assume what? Omega 0 minus omega is much lesser than the omega 0. But they are quite near. So, omega being omega 0 minus is much more omega 0. So, as a result, in fact, we will see a lot of components. But for our main task, we can do like this. We can assume what? Signal cosine time is a projection of the vector with amplitude and rotating with the frequency of him. Okay, rotating. The frequency omega heterodyne. It's a common trick on electrotechnics. Assume a harmonic signal as a projection of the vector on a complex plane. Signal at this moment I can represent my signal is, just 1 second, I will not the this one can also be assumed as a projection of the vector rotating its trajectory with the frequency omega 0. Result here is the result summary can be written as a square root of this one at this moment is OM, so M squared plus OH squared and minus double OA cosine of theta cosine of this angle. The maximum we will see something like this. One moment, where are we should get something like this. One moment. We should get something like this. Here it is on a small scope, so try to make it more stable. Stable. Something like this. So we will get something like amplitude modulated signal with the frequency being what kind? Difference of these two frequencies. How this angle changes? As a difference of frequencies. On the small scope, it's not very stable. Now I have only carrier, only, without modulation. What will be spectrum of some it will have as amplitude modulated signal central line at what frequency? Omega 0 minus omega. At the difference. When the difference is small, we will have not a difference of frequency small, but one signal is much larger than another one. We will see key moment at a difference. If we add, now I will turn. Yeah. Modulating signal, amplitude modulated signal at a frequency of 600 kilohertz. very chaotic. And we will see something like this. Let's do next trick. So I have, let's say, what's going on now? I have a source of omega 0. I have an amplifier which controls gain. Here I have my signal. And what I'm getting? Omega 0 and spectral lines of my signal. Here I have 400 or 405 triple 5 time and 5 hertz. Frequency 100%. Here I have rectangular signal. And here I have at one spectral line at omega 0 cosine with a frequency 600 kilohertz. Here at this point I have an amplitude modulated signal, rectangles filled with 600 kilohertz. What will be the next? Some with signal omega h local heterodyne. Guys, I will start repression. I have a local generator called heterodyne, and its signal is summed with my amplitude modulated signal. Next step is to apply a filter with transfer function like this at a frequency I will call it Fi, an interim frequency. Before the filter, signal contain what? Omega 0, omega heterodyne, and the difference. At this point, I would like to, what can I do? I can use this. I would like to switch the screen. Have yeah, I got it. One moment, I will connect this here. Very similar signals, isn't it? They are very similar. but there is one thing with the frequency. Original one was at 600 kilohertz. I have at this heterodyne. Wait 1 second, where's my line? This one should be real. What can I do? It's overranging. Oh, wait a second, I will use blue wire to show it. Here is signal of heterodyne, 900 kilohertz. Yellow line is a signal of. Now yellow line shows signal of this generator. It's adjustable. 900 kilohertz. And here it is. This one is at 600 kilohertz, and yellow one. Now yellow one shows this one. I have a filter with the frequency. It should be something like 470 kilohertz. The central line is approximately 470 kilohertz. Do you see what happened? This is spectrum of the yellow signal. Looks like amplitude modulated. Yeah? But at what frequency? This was spectrum of the blue line. And now, where is my... Yeah, here he is. And now spectrum of the yellow line. One moment, cursor. Do you see this? 472. Well, actually, it's 407. You see what happened? I got spectrum of this amplitude modulated signal, transferred to another frequency from 600 kilohertz to 400 without significant change. You can see they are like mirrored. There is a difference. This one at 600, this one at 400. It's idea of frequency transfer with the help of local signal source, mixer, and bandpass filter. I can transfer full spectrum without change. If I would use multiplier, if I would divider, spectrum signal will be distorted, spectrum will change. Here I have my signal transferred from one frequency to another without significant distortion. Its idea is behind very popular technique of super heterodyne receiver. Idea is what design a system for signal processing for one particular frequency is easy. Much easier. The system will be much cheaper when the system intended for a range of frequencies. But problem is what you usually will not be able to set one exact frequency. Usually you will work with a range of frequencies. With the help of spectrum transfer, it's possible to design system for one frequency called interim frequency. And before the main procession part, use a spectrum transfer technique with the help of local heterodyne and mixer. It's an old technique, it's used well, as we saw, but with two control grids. But there is one moment with this technique. Here I'm on 900. Take a look, I'm changing frequency. Should be the second one. Make it more. Second, I'm turning the wrong. Where are you? Oh, here it is. Super heterodyne technique has one problem. It's called a mirror channel. The frequency on which we receive spectrum is a difference of the signal, process signal, and the heterodyne frequencies. Here I have a relation. Or it's around, it should be. Here I have a signal on harmonics. It's a bit different. I got a signal on no, it's okay, it's a mirror. The idea with mirror channel, what there is two differences. When, see what's the problem. I have, in my case, heterodyne frequency was above signal frequency. I have result on a frequency of the difference. But there is another signal possible. In my case, heterodyne was above signal. But there is signal above heterodyne with the same difference. And it will form a mirror channel. I lowered the heterodyne frequency to get my signal on situation when heterodyne frequency is below signal. mirror channel. To suppress mirror channel or expensive high-rank system, use double frequency conversion. Not single, but double to suppress mirror channel. Hey, where are you? Oh. Very nice work of frequency converter. So idea of frequency conversion or spectrum transfer got your some input signal, maybe amplified, then mix it with the source of cosine or local heterodyne. In a case, you should select omega heterodyne minus omega signal equals to interim, it's I, interim frequency. Then apply a bandpass filter with the omega pass equal to omega interim, and you will, now you can build your process at the interim frequency by changing. How can you change frequency of receiving signal? Change frequency of heterodyne, and you will cut from the all possible frequencies one slice with the width of your filter. Use a band generator. Idea of spectrum transfer. What else? This one can be switched off. Also can be switched off. What can I show? Come on. Spectrum transfer. It would be nice to see a frequency modulated signal, yes? This one was amplitude. But how can I free some space? One moment, we will do something. So we would like to see a frequency modulated signal. But I have a problem. The problem is with, let's say, processing capability of my scope. I have a nice idea. I will use my receiver. I have interim frequency. Put it here. Okay, idea. I have a receiver. Good receiver. To process signal, my receiver uses a 4 megahertz interim frequency. Where is my a special adapter to get an interim frequency signal. Antenna. I'll check if it works, and then I need a test. I'll need a test generator. Power? Yes.
Нет, без 2+8 градусов.
Okay, this is good. I have what I'll do. I will bring at first a test generator. At first, let's see what happens with the ideal generator. old monstrous generator. It's a generator of frequency modulated signals. Domains. I will connect it to my receiver. I will connect it now. External. Just 0. Okay, I have a frequency set to 20 megahertz, so I need 20. Okay, here I have 20 megahertz here. And my generator produces 20 megahertz. But for this channel, what I'm using to make all this visible, I use ability of this receiver to transfer signal spectrum. Generator now produces pure carrier at a 20 megahertz, at a frequency of 20 megahertz. Receiver transfers it to its interim frequency of 4. See, it should be 4 exactly, but scope believes it's 4.1. Maybe it's true. Marking, here I have marking for, yeah, here I have at 4 megahertz. Signal of generator. No modulation is applied. At this moment, it produces pure carrier. Now I need what I need. I need to get a modulating signal. 0 to 0 carrier is okay. I need 1 second. I'll bring a wire. this. It's okay. Where is my U? U goes here, U goes there. And more wires for the god of wires. This one. Come. More wires for the god of wires. Which one is ground? Oh, yeah. Do we have a signal? Yes, we have a signal. Maybe I should use I will use modulating signal as a synchro source. Just need an adapter. Come on. Oh, here it is. What do we see now? Is it something familiar? Did we saw something like this before? modulating signal, our rectangles, and modulated signal. At this moment I'm using amplitude modulation. Carrier is at frequency of 20 megahertz. But to make it visible, I use this receiver to transfer it to 4 megahertz, to interim frequency. Our spectrum, as we saw it, I can switch off higher harmonics. We see modulation, amplitude modulation with harmonic signal. And scope isn't very happy. Maybe I can help a bit. See, I'm changing adjustment frequency of the receiver, and what changes? Frequency where the spectrum is transferred. I think this one is good. You can see it takes time to recalculate, but arrives side band of this nice sign. Transfer to interim frequency. Amplitude modulation. Nice. I can add higher frequency and we see them. Now let's switch to frequency modulation. This one is all AM. Not modulated, one single carrier. Maybe second, I'll bring here it is. I'll bring it to the center of the screen. Near zero modulation, we have one central line. Small, only couple of percent. Do you see? Two spectrums unmodulated. I'll bring it to the center to make it easy. Here it is on the center. modulation. Very small modulation index. You see, spectrum of signal arrives symmetrical relative to the central line. Deeper. I need to change scale. At this moment, I larger frequency deviation. Now it's forming a class of FM signals. Frequency modulated signals. Omega 0, you will see something like this. Not good. Peak, degree, peak. 0. Omega 0. Something like a suspension bridge. Unmodulated signal. Small depths of frequency modulation. Wide. Receiver allows me. Wait 1 second, please adjust. Some 300 kilohertz now. And case for comparison, amplitude modulated signal. With the same approximate adaptive modulation. You see difference in frequency range. Frequency modulation requires much broader frequency range. Amplitude modulated, frequency modulated. I'm not sure. In theory, I can try to it's virtually impossible to get it visible in time. No modulation. In time, it's virtually impossible to see. Here, in different. Hey, come on. Here, in different scale, we see one. Maybe I use small. Very small depth of modulation and scale as wide as possible. See what's going on. Viewer sine, adding. We will set at center with No. This is amplitude. Amplitude modulated. Wow. Come on. And this is frequency modulated signal. Without, it is pure sine, adding third and fifth harmonics. These are spectrums of the signal. With more deeper modulation means wider and wider spectrum of the signal. So frequency modulation isn't effective when we speak on the, let's say, use of frequency range, but it ensures much better quality. And now I would like to show, I have time, a real signal. I will disconnect. Generator. And I will touch aerial antenna. We have sounds and we have something we can analyze.
Kā jūs teicat, manuprāt, tur ir spēcīgas diskusijas bijušas starp Brehtu un arī tajā, ko viņš raksta. Viņš jau visu laiku uzsver to, ka nevajag radīt šo ilūziju. Vajag visu laiku spēt rādīt tēlu un vienlaicīgi viņu komentēt, viņā neiepūst. Pilnīgi citāds domāšanas veids, veidojot šo izrādi kopumā un spēles veidu. Tā kā, es domāju, tas noteikti ir izaicinājums. Starp tiks un vajadzētu skatīties kāds ir.
Brehta teksti tagad ir pieejami latviešu valodā arī?
Lūgas ir bijuši pieejams jau ilgstoši, sens izdevums ir no 60 gadiem, es nemaldos. Tas, kas manā priekšā ir, tas ir mazais teātra organons, Brehta tāds teorijas apkopojums, un tas arī bija
4 megahertz. Sorry, I switched to it then.
Nu, tev atver lūgtūkoļu, ļoti jāpārskata un jāparediģē un jāmodernīgo.
Un te atkal ir jautājums par to, kur mēs
Something.
valstiskā līmenī nekāda tāda atbalsta.
Can I get this signal
Procesam nav, un mēs
after
saskaramies ar to antoloģijas kontekstu.
demodulation?
Tiešām vēlos problematizēt un uzsvērt, ka vienkārši trūkst tulkotāju no vācu valodas, kas kvalitatīvi var iztulkot sarežģītākus tekstus, teorētiskus teātra tekstus, bet es arī domāju, arī, lai atrastu lugu tulkotājus, būtu tiešām pamatīgi jāmeklē, ļoti specifiski.
Šobrīd mēs runājam arī par to, ka varētu trūkt skolotāji, gan vācu, gan franču valodas, bet tas varētu būt
Signal we're receiving.
atsevišķi
It's a sound
Kultūras
we are hearing now.
klausās.
Daudz, kas no tā iepriekš pieminētā no aktieriem. Tātad aktrises Milena Škeviča
Look at the spectrum.
Jāšveido aktrise Milena Škeviča. Viņa ar Breta Baileru saskārusies jau diplomāta izstrādē Lepenās kāzas, ko iestudēja Indra Roga un Kārlis Krustovs.
Oh, I got it freezed. Can you see? I have freezed. 1 kilohertz. What's it looks like? Sound, simple sound, isn't it? This is signal of radio broadcasting on FM. Sound. 8 kilohertz, 9999. And what about this? Shows 19 kilohertz. Can human hear it? Shows 19 kilohertz. No. I need to compress spectrum. See, we have sound area. I can find different station. You see this area? Noise. Again, sine, something at 19 kilohertz, and something above.
Вот это элемент.
Some block. You see the spectrum? Sound, something at a cursor, and looks like another sound, but in not hearable area.
What is the limit for the human hearing?
I cannot give exact answer because actual for young guy it would be something like 15-16 kilohertz. But ability to hear
No, of course, it decreases.
it deteriorates with the age. For a guy of my age, it will be some 8 9 kilohertz. It goes down. I would like to draw a spectrum of what we see. We are not studying communication, but it's for it's just for idea. Where is my table? One small. First one. See, idea. If we need a good quality of sound, we need to transfer what? Left and right. Because human has 2 ears. Oh, it's the signal what we see is not a very simple signal. It's first part. It's a so-called complex stereophonic signal. Idea. I have left channel and right channel. Till 15 kilohertz. I have a frequency area for traditional monophonic. It's left plus right signal. Nice, but it's not enough. We need left minus right. From the 38 kilohertz spectrum of left minus right, left minus right, is transferred to interim frequency of 38 kilohertz. But do we see? Where is my cursor position? Here is 38 kilohertz. Come to center. Do you see anything at the red line? No, we see a gap. The idea to prevent, let's say, to save energy, carrier of the signal is not transferred. It's a balanced modulation. Originally it was, at the beginning it was AM, 38 kilohertz, and spectrum of left minus right left minus right. But before broadcasting, carrier frequency was removed. It saves energy and reduces crosstalk. But how can we demodulate this signal? We need to know where the central frequency was. To do so, at a frequency of 90 kilohertz. 1 second, I'll move. I'll move to 19. It is 19 kilohertz. Sorry, I'm in the wrong place. Here is my 90 kilohertz signal. Bring it to center and here it is. See this peak? I enlarged it. It's so-called pilot tone. At 90 kilohertz, so-called pilot tone is transferred. It's a free frequency. It's used to recreate a 38 kilohertz carrier to demodulate, to, or say, unpack from. See what's how signal is packed. Sound one left plus right. Then with the balance modulation, left plus right put at around 38 kilohertz, and all this used as a complex signal to modulate, in my case, what a frequency. Where am I at this moment? 99.4 megahertz signal, and then it's transferred to us. But nowadays it's not so simple. This is point around which balance modulation is building. But what's this? What's on the higher frequencies? The signal is more complex. Much more complex. I need H56, yes, I'm in the right position. something goes on around 56 kilohertz. Actually, I need a central point of 57. I will go to 57. See, around sporadical something arrives around my center line. We are live today in a digital time. So, lower 30 hertz, upper 15 kilohertz. This is left plus right, monophonic sound. 19 kilohertz, pilot. 38, suppressed carrier, around it, left minus right, left minus right. And next one, triple pilot. What it should be? It should be 57. This one ends at 53 kilohertz. And what about 57? RDS. Here around red line, data stream appears. It's the name of the station, track playing, weather, and so on. Maybe I need to find. Here at 57 kilohertz, periodical arrives signal. It's at take from the LDS. was so big. Actually, yeah, it should not be very large, only 5% of energy. I would like to find one with the well visible data stream. This is my 19. Pilot is okay. 50. Here should be a date for what is for 38. Yeah, it's at the center of the balance modulated. Maybe no signal is weak. This will suppress everything. I don't know why. Noises. This is not changing everything. I can do. I can help a school. have said the central line should be at 38. Maybe. It should look like double, like a camel back. And the next one I should see. Oh, sorry, I'm not. Here is a center for data. There should be a data channel. You see a lot of noise. Strangely, we see signal further. There is another data channel at 76 kilohertz. But it should not be occupied. Okay, key idea. Time is going out. Key idea. What FM, first, we can transfer spectrum, it's one. And second key idea, what frequency modulated signal will look like this, depending on the depth of modulation. Yeah, we are running out of time, so I will